In this video, we're going to be talking about IP version 6 and giving a broad overview about some of the components that go into IP version 6. In this video, we're going to start out by talking about the history of IP and IP version 4 and how it came about where we needed IP version 6. Then we'll get into the specific reasons for IP version 6 and why it needs to come in and rescue us from IP version 4. Then we'll talk about IP version 6 formatting. What does the IP address look like? Just a brief overview of what you would see when you're talking about an IP version 6 address. Then we'll talk about specific IP version 6 address types. Once again, it's going to be an overview of the different address types that you would expect to see with IP version 6. Then we're going to talk about assigning addresses, how we assign addresses to machines when they start up, how they actually get the IP version 6 address. And then we will briefly introduce what Neighbor Discovery Protocol is, NDP, because that's a key component to IP version 6 and how IP version 6 functions. Looking at the IP address history lets us know why IP addresses are the way they are and how they function. In a prior video, I talked about IP version 4 history and how it was developed over time. So I'm not going to go real in depth into this, but I'm just going to mention a few of the highlights of that video. So one thing we talked about is those RFCs and how it defines different functionality and how this is set up. So we talked about specifically one of the first iterations of IP version 4 was RFC 760, where it talked and defined how IP version 4 addresses looked. And with that, it just said, well, these first few bits, these first 8 bits is the network, and the last 24 bits is the host portion of this. That clearly doesn't allow for as many networks as we have, and that was way too many hosts for the networks because those hosts can, having that many hosts on the network can burden it and it cause problems. So then very quickly 791 came out. And 791 started defining, well, what we'll do is we are going to allot some of these addresses, some of the address space or the scope. We're going to say, well, those are class A, so they're only the first 8 bits is going to define the network. And then we'll have a class B, and the class B, it'll be the first 16 bits will define the network. And then we have a class C, and that means that the first 24 bits will define the network. And then there's a few others as well on top of that, but that's just the highlights of that RFC 791. Then we said, well, that's still not giving us enough flexibility. So then RFC 950 came out, and when 950 came out, it said, well, we'll still use this classful system in here with A, B, and C, but we can further break down those networks by doing subnetting. So RFC 950 introduced subnetting, and so you can start breaking these big networks, these class A's down into smaller segments, or class B into smaller segments, or class C into smaller segments. Then we see a couple other developments with RFC 1817 and 1878 having to do with, around the same time VLSM came out, CIDR notation came out, classless routing came out. So around the same time, there's some different RFCs that came out, and it pretty much said, well, now you can really vary this up and you don't have to be so strict with your subnetting, so you can actually have variable length subnetting. And it got so that it took a lot of these boundaries down. And we along the way, each time we run out of addresses and start looking at, okay, how can we further utilize this IP version 4 space, this IP version 4 scope? And then we developed RFC 1918, and RFC 1918 then created some private addresses, and those private addresses then can be used on your local area network, but then they get translated into some sort of public address when it goes out the router or the firewall. So that's where we get natting and padding involved into that. So then that worked for quite a while. That gave us definitely some momentum with IP version 4 and able to extend out the use of IP version 4, but we're still running into problems with the IP version 4 scope or address space, and we need more. So that is the reason for IP version 6. It is the solution to giving us a lot more time with IP addressing and able to equip us with the future needs, and that we continue to need more address space. So how does IP version 6 help with this? Well, there's actually a lot of reasons why IP version 6 really helps out with equipping us for the next stage in our network communication. There's a lot of efficiencies and security that comes involved with this, and so we'll talk about all of those efficiencies and things that are involved with making IP version 6 what we need moving forward. But the really big thing is it just gives us a lot more scope, a lot more addresses that we have to work with. When we created IP version 4, there was just no idea that it was going to be as big as it is. And so we need now a much bigger address space. And to give you an idea how much bigger it is, IP version 4 uses 2 to the 32nd power. There's 32 bits. So 2 times 2 times 2 times 2 times 2, 32 times, which is pretty big. I mean, when it was created, it was thought of, well, this is going to last us a long time. And truthfully, it did last us a long time. But now with the explosion of the amount of end devices that need IP addressing, we need a new system. So where the new system comes into play is IP version 6, and it is 2 to the 128th power. So it is an incredible number, a much larger scope, a much larger space that we have to work with. And so that is the biggest reason why IP version 6 is needed and why we implemented IP version 6. So what does an IP version 4 address look like? Well, it is very large. So this is an example of an IP version 6 address, and we'll go more in depth into a future video of all of the components of this. But really, just from a highlight standpoint, each one of these is called a hextet. It actually goes by several different names, but generally speaking, we call this a hextet. And each one of these bits is a hexadecimal number. And so a hexadecimal number, so this 2 right here is actually 4 bits. And this 0 is another 4 bits. And this 0 right here is another 4 bits. And this 1 right here is 4 bits. So each hextet is 16 bits long. And so you can see that 16 times 8 here is 128. So we've got a lot more bits that we work with versus IP version 4 is just the 32 bits. So we, generally speaking, now this can vary and it can change, but generally the last 4 hextets are the host side, or what we call the interface side. It defines an interface. And the first 4 here is what is the network portion. And so we have a prefix that will define where that line is. So in this case right here, the prefix is 64. So it defines that this is the 64 bits on this side, which is the network side. And then on this side, we have the host side. So that's a little bit about the IP version 4, or IP version 6 address and what it looks like. Just a note here though, is those IP version 6 addresses don't need to look that crazy. It could be as simple as this. And once again, in a future video, we'll talk about how we can concatenate or shrink the address and what the address looks like. But this would be an example of just a really short address. This happens to be a multicast address, but this is a short address that does exist. So what are the different address types? Well, a few of the big address types here, some of the categories is unicast. The unicast, remember, is one device is sending data to another device. It's a specific device on the network. It could be a remote network or it could be something locally. So that is a unicast address, is a one-to-one. Then we have a multicast address. The multicast address, similar to IP version 4, well, it's pretty much exactly the same thing, is a device to many different devices. So when this can send out a multicast address, and it could potentially go to multiple devices that are on the network, either the local network or possibly even outside in a remote network. So we've got a multicast address, which would be one to many devices. Then we have anycast. So the anycast is similar to a multicast, except for it's going to go to the first available device. So where you have with a multicast, could be sent out to many different devices at the same time. And anycast is there are many devices that can help this device or can facilitate this device or can respond to this device, but it is only going to go to one of those devices. So perhaps there's multiple servers or multiple, let's say, routers that are on this network here. And it could respond to this machine right here, where a multicast may go out and hit every single one of those routers. And anycast, the switch is only going to forward this on to one of those devices. And it's going to be the first device from a path standpoint. What is the closest device? So it's going to send it to the closest device. So it is still a one-to-one, but it has multiple options to choose from. So that is the anycast. Notice that there is no broadcast. So within IP version 6, broadcast has pretty much gone away. There is no broadcast address that gets sent out to all devices. However, there is a multicast address that can look much like a broadcast, meaning that most devices are going to subscribe to that multicast broadcast or that multicast address. And so you can send out to a lot of different devices, but it's still considered a multicast. It isn't a broadcast. All right, let's get a little further into some different unicast options that we have, different unicast addresses that we have. So first of all, we have a link local address. A link local address is similar to like in IP version 4, if we have an IPv6 address, that's the addresses that automatically get assigned to your devices when there's no DHCP server. So you start up a Windows machine, it doesn't find a DHCP server, so then it will automatically assign a 169.254 address to it. And that is the IPv6 address, the link local address. So this is similar to that. It's an IP version 6 link local address, but in IP version 6, they're much more important. They play a very critical role with IP version 6 addressing. So we're going to talk about link local addresses and how they function. Then I'm going to jump to this global unicast address. A global unicast address is just a public IP address. So in IP version 4, we just call them public addresses. They're routable on the internet. That is what a global unicast address is, or a GUA. And we are going to definitely get more in depth into what those global unicast addresses are as well. Then we've got the unique local. So the unique local address, let me just give an example. This link local address can only go into this local area network. It will not go beyond this router. Whereas a global unicast address can go out to the internet and to the outside world. So let's say then this is all some privately owned network right here. The unique local cannot be sent out to the internet. It's not routable back to this network at all, but it can be routed within this private network right here. So that is a unique local address. You can think of it similar to the private addressing that's in the IPv4 space. You know, that's the 10.0.0.0 network, or the 172.16 networks, and then or the 192.168 networks. So it is the private addressing that happens. The difference with this, though, is it's never intended, was never developed to be translated to the outside world. So it only stays within your local network here, meaning your privately owned network, and is not meant to be routed out to the internet. So now, how does your machines get all of these addresses? How does it develop them? Well, the link local address, it has a couple different methods of actually creating it. One is we could randomly assign to it. Windows machines randomly assigns it. Another option is like Cisco equipment by default will use the EUI64 to assign addresses to that link local address. So there's a couple ways that the link local address can get generated, and we'll talk about those different ways. The other one that I just want to mention is the global Unicast address. The global Unicast address can be assigned several different ways. One is we could statically assign it. So we could statically assign an address to a machine, and then that will be the address that it uses. The other way is we talked about a little bit about DHCP. DHCP is a IPv4 protocol, and it's used to assign addresses to a machine so that way it can get out to the internet. So that's the DHCP server that will assign those. Well, there is a DHCP version 6. And so the DHCP version 6 is the equivalent to DHCP is for IPv4. You have DHCP version 6 for IPv6. So you do have that. Another method is using SLAAC. And we are going to get more in depth into what SLAAC is. It's the recommended way now to assign IP addresses to machines. And so a lot of this course is going to build up to that point where we can discuss what SLAAC is, and so we understand what SLAAC does and how it operates. So we will definitely be talking that as well. Sometimes we actually couple these two, and we use SLAAC, but then it also references some DHCP options. So we can actually use those in combination with each other as well. So we'll get more in depth into that as we go along. Your machine needs a global unicast address for it to be able to get out onto the internet and have information be able to be returned to that machine. And so you need an address that's capable of doing that. That's why it's called a global unicast address. So somehow it needs to get that. Well, the answer to that in the past with IPv4 was a DHCP server. I've already mentioned how SLAAC can do that, but that's actually a little misleading. SLAAC doesn't assign IP addresses to the machine. In fact, SLAAC this protocol allows a machine to assign an IP address to itself. That's very interesting on how that works. It assigns a globally in the world, a unique address to itself. And so this is how it does that. It's kind of crazy, but yes, it's assigning a globally unique address to itself. And how it does that is it has these interface bits. The last 64 bits of this address right here is the interface bits on this. And your machine already with the link local has a mechanism to generate something that's going to be unique on the local network. And so this right here gets generated somehow, either randomly or through the EUI64, gets generated, and it's unique to the network. No other machine on the network has that address. And so then all it needs then to function is it just needs to know what network it's on, and then it's got a globally unique address to it. And so what will happen is it will, through neighbor discovery protocol, it will send out some messages and do what's called a router solicitation and ask the router, hey, what network are we on? And that router, it will reply to it and it will give it this information right here. And then it will take this information, tag it onto the information that it's already generated, and now it is a global unicast address. It's unique to the world. And so that is how SLAAC works. We're going to get much more in depth into how it functions and how it works, but generally speaking, that's how SLAAC works, and the machine is able to generate a IP address that's specific to that machine, that's unique and doesn't overlap with any other machine out there in the world. And that SLAAC is facilitated. The reason why it's able to do that is through this neighbor discovery protocol. Neighbor discovery protocol is something that interfaces with IPv6 capabilities, uses to actually do some configuration and create that global unicast address. And it can also do some other discoveries on the network. It's a replacement for ARP. So IPv6 does not have ARP. And so we somehow still need to find out the MAC addresses. So neighbor discovery protocol does that as well. And so as we go through the next series of videos, we're going to start building upon these concepts and learn how the link local address plays into the neighbor discovery protocol, which plays into the doing the router solicitation and getting a router advertisement back, and then that plays into the SLAAC and how SLAAC operates. So we'll just continually go through this and build upon this information that we just talked about here. All right, so what we covered, we talked about IP addressing history, gave a brief overview and how we kept creating a new standard, and then we ran out of spaces and we created another standard and ran out of spaces. And that led into finally saying, well, we've exhausted IP version 4. It is time to create a new standard. And that's where IP version 6 comes to the rescue, because it gives us just a huge address space to work with. We also talked about some formatting with the IP version 6 and how the IP version 6 address is formatted. We talked about some different address types with IP version 6. We talked about address assignments and how assignments happened and how they're with those different address types. And then we wrapped it up talking about neighbor discovery protocol. Each one of these concepts in the future videos we'll get more in depth into. I hope these videos are really helping you out. If they are, I'd really appreciate you hitting that like button.